In this lesson, we are going to introduce Newton's method. And Newton's method is for approximating roots. So when you take some sort of a function and set it equal to 0, you're finding the zeros, also known as x-intercepts. So when we do this, we're going to try to figure out, get a rough idea of where one of our solutions, our x-intercepts or 0 might be. And then we're going to do a bunch of iterations of this to create more and more accurate x-intercept or solution. So the idea is we're going to kind of walk through it and we'll kind of compare it to what this visual is representing. So first thing is we have some sort of a cubic and we need to figure out where to start. So to start is, I don't know what this looks like. I'm going to try to not use a graphing calculator. I'm going to use a calculator, but not a graphing calculator. I'm not going to use the graphing piece of it. So if I have no idea where to start, I'm going to start by getting an estimate. And so I'm going to kind of go back to college algebra pre-calc, and I'm going to start plugging in some values and seeing what's happening. So if I plug in a 1, I don't know if you remember that you can just plug 1 in and get a y value, or you can do synthetic division. And so if I kind of use this, I have a 1, 1, 0, 1. So if I work through this, remember that the y value, or this remainder that I get, is actually the y value. And so I could just be plugging it in to get the y value, but sometimes I get numbers that are a little out of control. So this might keep the numbers a little more at bay. So if I drop the 1 down, this is 1, 2, 2, 2, 2. I get a remainder of 3. All right, so I'm looking at a 1, 1, 2, 3. Okay, so somewhat close to the x-axis. So I don't know if I should go to the right or to the left. I don't know. I'm going to plug in, well, I know if I do a 0, I'm going to get a 1. So how about a -1? So I'm heading in the right direction if I went to the left. And so if I plug in a -1, 1, 0, 1, I get, bring the 1 down, I get a -1, a 0, a 0, a 0, a 0 adds up to 1. All right, so I'm getting closer, heading in the right direction. So if I do a -2, I kind of go through this again. I'm looking at a 1, 1, 0, 1. So if I do synthetic division, I get a -2, -1, 2, 2, -4, -3, which that means I had to have crossed the x-axis somewhere in between -1 and -2. Right, so that gets me my starting point. I need something that I know is somewhat close to an x-intercept. And so this is a way for me to do that, is I'm looking for how my y values transition from a positive to a negative, or a negative to a positive, means I cross the x-axis. So I'm going to start with a -2. So for Newton's method, we are going to just use this formula. So this means our next x is based on the previous x minus the y value for that x divided by the slope at that x. All right, so what I need is, I have my original function. I need my derivative. My derivative of this would be a 3x squared plus 2x. And I need to start this process. So my initial x is, I'm just going to go with a -2. And then I just plug it into this. So I'm going to do my first x is going to be me plugging in a -2 minus f at -2 divided by the slope at -2. All right, so if I do that math, -2 minus the y value I just found over here, -3, divided by, if I plug in a -2 into this, I get a 4 times 3 is 12. 12 minus 6, 12 minus 4 is going to get me an 8. So if I plug that in, and I'm going to be adding that to the -2, I get a -1.625. So that gives me an approximation. So here's what happened. This is creating an x value kind of based on a tangent line. And so what we did is we plugged in a value, we found a slope, And this x that we're getting out is the x-intercept of that tangent line, right? So what we're doing is now we're going to plug that in, and then that's going to bring us to another x-intercept, which is going to squeeze and get closer and closer and closer. So then we're going to take that x value, plug it in. It's going to create a tangent line. And so we're going to get another x value. And so we're going to get closer and closer and closer and closer to our actual x-intercept. So we're going to do a whole bunch of iterations on this, and we're going to stop doing this by hand. We're going to show you how we can do this with a calculator. So far we know that our first value is negative 1.625. So, sorry, negative 1.625. So our second iteration of this is going to get even closer. So let me show you how we can use a graphing calculator for this without doing the graphing part. So I need to figure out how to work through this process right here more efficiently, because I don't want to do it all by hand. So what I'm going to do is I'm going to create this equation, right? But I'm going to do a couple things. I'm going to plug in this function into one of my equations, ideally y1. And so I have x to the third plus x squared plus 1. And then I'm going to put my slope in, x to the second plus 2x. All right, so I have that, and I have to remember that my original one is y1, my slope equation is y2. Clear out of that. And then I'm going to basically write x minus, then this as a fraction is going to be, that was my y1. So I'm going to do alpha. F4 is a nice shortcut to get my list of equations that I plugged in. So y1, and then at x. So it's going to plug in whatever I plug in here, it's going to plug it in to that function, and then divided by the y2 times at x, right? So right now, I don't know what I have x stored as, and so it's going to give me potentially some value. I think I've already prepped it to be stored as -2, but so here's how I made that happen. I wanted my first value to be -2. So I went down here and I went -2, okay? And then I want to store it as x. So it looks like that on the screen. So then I store it as that, and then I can highlight that formula and let it do its thing. So now I'm going to store that value and let it run, right? And so I'm going to take this and I'm going to go that value stored as x, and then I'm going to let it run its thing. Okay, and so I'm going to start to squeeze this value. And so I'm going to take all the decimals to this, negative 1.485785953. And then I'm going to store that value. So I'm going to store, so it's going to take that answer and store it as x again. Then I will go up and run it again. And what it's constantly doing is the visual, is it's getting me an x-intercept, and then I start this whole process again, and I get another x-intercept, and I get another x-intercept, and it's squeezing it. And so my third iteration is, I missed a 1 in front of that, negative 1.46595592. And then I'll store it again as x, and then let it run. So what you're going to see is you're going to start to see this repeat. And I'm going to do it until I have everything that repeats. So for some level of accuracy that we're looking for. And so that level of accuracy I know is when my values are not changing. And it may be out to 5 decimal places or further. It just depends on whatever the directions are asking for. So right now I'm seeing that I got a 465. That's pretty locked. And then I'm going to keep on going. So I'm going to store that one as x. And then I'm going to let it run again. And now I'm getting my fifth iteration, negative 1.465 5, 7, 1. And then, so all of that has been the same. And then here's where it starts to change. 2, 3, 2. And so then I'll do maybe one more. Feeling like by now it's going to start to kind of lock all the decimal places. Let it run. And I'm getting the exact same thing. So that is as accurate as I can get up to that many decimal places. Right. And so there is my x-intercept. And then if I cheat this and kind of check it, and I go back, I'm going to turn that off, and I'm going to graph it. Right. So there's that value. I knew it was somewhere between a -1 and a 2. So that value kind of agrees with that. And then if I actually go and find this x-intercept left and the right, guess I'm getting a value that I get a 1.465571, 1.465571. Right, and even ours went even more accurate than what the calculator gave on the graphing calculator. Right, so that was a little bit of an introduction to Newton's method. First off is you need to figure out a value somewhere to start. We don't want to just randomly start somewhere because you have some efficiencies that will happen if you can get close to an x-intercept. And that is basically finding somewhere where you know the graph passed through. And so we could have started with a -1 just as easy as starting with a -2. Both of them are pretty close. We might have saved a step potentially if we did a -1. But in the end, it's not that long of a process if you have a graphing calculator, then kind of help the cause of it a little bit.